This video is going to look at finding the zeros of polynomial functions. Our first example we have is f of x equals x squared times x plus 5 times x squared minus 9. Well, we know that if we're looking for the zeros, we're going to set your function equal to 0. So we have x squared multiplied by x plus 5 times x squared minus 9, and we're going to set the function equal to 0. So we want to know what x value is going to make this entire function go to 0. So in other words, our y value is 0. What x value is going to make the y value 0? Now here, don't make the mistake. A lot of people make a mistake here and multiply this out. But remember, if we're solving for x, we're in luck because here the function is already factored for us. So all we have to do is set each factor equal to 0. Now we can take this and we would have x squared, so we can think of that as x squared equals 0, x plus 5 equals 0, and x squared minus 9. Now there's two ways we can do this. We can take x squared minus 9 and we can set that equal to 0. Or if you take x squared minus 9, we could always factor this, and this would factor as a difference of squares x plus 3 and x minus 3. So that's two options you have here. Now, how do we solve each one of these for x? Well, x squared equals 0, then that's just simply going to be x equals 0. X plus 5 becomes x equals negative 5. And then we would have x squared equals 9. And don't forget here, if we're solving for x, we have to take the square root. And when we take the square root, that's going to become plus or minus. So that's where we get x equals a positive or negative 3. So we have 0, negative 5, plus or minus 3. And again, over here, this is where you would get your two answers, plus and minus 3. If you set each one of these factors equal to 0, you would have a negative 3, and you would also have a positive 3. So you could simply use the technique here, take the square root, or if you factor this, you would still get the same plus or minus 3. Now, keep in mind, we found the zeros of this function. So if we look at this graphically, what have we just found? Well, if we take your calculator and we go to y equals, and we graph this particular function here, we would have, let's see, x squared, x plus 5, x squared minus 9. So if we take x squared, and then that's going to be multiplied by x plus 5, x plus 5, and then we have x squared minus 9. And if I go to zoom 6, zoom standard, here's our graph. And we're going to have to adjust it. Notice the graph's going up here off the screen and then going down. So we can go into the window and we'll play around with the screen here. And we want to adjust the y because it's not going up high enough or low enough here. So I'm going to make this a negative 50 and try a positive 50 and see what we come up with. And even there, it's not quite high enough. So let's go back to the window. And let's try negative 65 and positive 70. And we still need to go higher, and it looks like we still need to go lower over here as well. So go back and adjust the y. And I'm going to go ahead and make this negative 80. I'll tell you what, let's just go make it a negative 90 and a positive 90. See what happens. All right, still need to go further, so let's go back. So let's go a negative 125 and a positive 125. Whoops. Domain, let's go back to the window. What did I typed in two negatives, so let's see. This should be a negative 125 and a positive 125. All right, so we're up high enough, but we still need to go a little bit lower. So if I go back to the window, let's try negative 150. All right, so that's a pretty good picture of the graph. And if I copy and put this over into our notes here, what we're looking at is we found the zeros. Well, that's where the y value or the function is equal to 0. So what we've actually found is right here, 1, 2, 3, 4 answers. In other words, the graph crosses the axis in 4 places, and that's why over here we have 1, 2, 3, 4 zeros. And if you look closely, because we have 1, 2, 3, and 4 zeros, we have a plus or minus 3, so that's 2 different numbers there. If you were to multiply this out, we would have ended up with what? X to the what? We have x squared, and another one here. So if we'd have multiplied all this out, we would eventually had something with a x raised to the 5th power. So that tells us we're going to have 5 zeros. And if you look here, this x squared, because of this one, this is really a repeated 0. Okay, we talked about this before here. If this is a repeated 0, it's an even number of times, and that's right here at the origin. That's why the graph goes up and comes back down. Notice it doesn't cross through the axis like it does at the other zeros. So here we technically have 5 zeros. It's just one is repeated here twice. So you have 1, 2, 3, 4, 5 zeros. All right, so we could have found these zeros instead of factoring, which in this case it was already factored. We set it equal to 0 and solved. We could have went to the calculator and we could have calculated each of these zeros that way. But I want you to understand how we can find the zeros here algebraically as well. So here we have our next example, and once again we notice here that it is already factored for us. So all that we have to do is take the function and set it equal to 0. And also you'll notice here that we have two factors that are complex, so we're going to end up with 2 complex zeros. So here we're simply going to set each factor once again equal to 0. And then we can simply solve for x. So here we would get x equals a positive 4, x equals a positive 3, and there's our 2 real zeros, and then we have x equals 2i and x equals a negative 2i, which would be our complex zeros. So here we have our 4 zeros, and I want you to notice if we look at the original function, we have an x times an x times an x times an x. If we were to multiply this function out, eventually we would get x to the 4th power, which means this exponent says that's how many zeros we have. And notice we have 1, 2, 3, 4 zeros. Now, what's going to happen if we graph this particular function? Well, in order to graph this function, I'm going to take f of x. We have x minus 4 and x minus 3. And then I want to take the last two here, the x minus 2i, x plus 2i, and I want to multiply those together so we can get rid of the I term. And if we multiply this out, you're going to get x times x, which is x squared. And when we multiply the outside and the inside, you're going to get a positive 2xi and a negative 2xi. So the middle term is going to cancel. And when we multiply the negative 2i and 2i, you're going to get a negative 4i squared. And the I squared, remember, is a negative 1. So that means a negative 1 and negative 4 makes this a positive 4. So down here, we're going to get x squared plus 4. So if we take this expression now, And let me go ahead and point this out. If we have x squared plus 4, let's think if we were to solve that now. If we set x squared plus 4 equal to 0, and we were to solve x squared equals negative 4, what happens when we take the square root of both sides? This is where you get, x equals plus or minus, the square root of 4 is 2, because it's a square root of a negative, that makes it I. So that's where we get the plus or minus 2i. So when you take the square root again of this negative number, we get the complex 0. Now back to the main part of this. I said, why did I multiply the x squared plus 4 out, or the x minus 2ix plus 2i, to get x squared plus 4? So now we can go to the calculator and put this in, x minus 4, x minus 3. So let me go to y equals here and clear out. We would have x minus 4 and x minus 3. And then we have x squared plus 4. So all I did was type this into the calculator, x minus 4, x minus 3, x squared plus 4. And I'm going to go to Zoom 6, Zoom Standard. And notice here's our graph. We have like a parabola here opening up. So if I copy this into our notes here, and this is the part we want to, again, notice what's happening here. We said that we have a total of 4 zeros, but if you notice, our graph only crosses in 2 places, and that's here at 3 and 4. Notice the 2i and negative 2i, that's a complex 0, so that doesn't show up on the graph. So notice here we have 2 real zeros and we have 2 complex zeros. So once again, we have a total of 4 zeros. Now the calculator will show you the real zeros, but the calculator, or the graph rather, will not show you your complex zeros. All right, if we move on to the next example here, we have f of x equals x cubed minus 13x plus 12. Now here we're doing the same thing. We want to find the zeros of this polynomial function, but this time it's not factored for us. So how can we go about trying to factor this? Well, there's not really a good way to factor this because we don't have an x squared. We have x cubed minus 13x plus 12. So there's not a really good way to factor this, but there are some techniques that we can use to help us break this down. Now, I'm going to go through a technique that your textbook's going to show you, and it's going to show you how we can find, and be careful here, it says possible, keyword is possible zeros. Okay, and the way that we can find possible zeros is we're going to look at up here. Let's start with the positive 12, and I believe your book uses the letter P to represent this. What are all the factors of 12? Well, that would be 1, which would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So these are all the possible numbers that will divide evenly into 12. 1, 2, 3, 4, 6, and 12. And of course, they could be positive or negative. Now, I want to look at all of the possible factors here. What's the coefficient of x cubed? This is our largest exponent, so it's a 1. What are all the possible factors of 1? And that's going to be our q. Well, here there's only one factor, or 2 would be what? Plus or minus 1. The possible zeros that we're looking for is going to be all of the possible combinations of p divided by q. So that means I'm going to take 1 over 1, 2 over 1. So notice here, we're just going to end up with plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Now, because this q was a 1, then really the possible zeros just turn out to be all of the possible factors of this 12, which is our constant term. So we just have here, these are all the possible zeros. Now keep in mind, they're not all the zeros, they're just possible zeros. Okay, and if we look up here, we know that based on the exponent, our largest exponent up here is 3, so that tells us the actual number of total zeros that we can expect to have. Now, when I say that's the number of total zeros, that's looking at imaginary or your complex and your real zeros. Now, really before the invention of the calculator, we would go through this technique here to find possible zeros. And once we find possible zeros, we would take these zeros and use our synthetic division. And for example, I'm going to pick the -1 here. I'm just going to randomly pick one of these values. So I'm going to take -1 and use synthetic division here. So up here at the top we have what? X cubed. So that's 1x cubed. So I'm going to bring down the 1. We don't have an x squared term, so that's 0. And then we have x to the first, so that coefficient is a -13. And then we have our constant term 12. So I'm just randomly picking a possible 0 and seeing if this actually is a 0 or not. Well, we bring the 1 straight down. -1 and 1 is -1. 0 and -1 is -1. -1 times -1 is 1. And then we have -13 and 1 is a -12. -1 and -12 is a +12. And 12 and 12 equals 24. So therefore, because we don't have a remainder, this is -1 is not a 0. So at that point, we would go back and we'd pick another number. So I'm going to try a +1. Let's see if that works. So we still have 1, 0, -13, and 12. Bring the 1 down. 1 times 1 is 1. 1. 1 times 1 is 1. And now we get a -12. 1 and -12 is -12. And now we end up with a 0. Remainder is 0. So that means that here x equals 1 is a 0. Now, what's the advantage of using the synthetic division? Well, remember up here, just like we did before, we started out with an exponent of x cubed. So once we divide, this is going to drop down 1. So that means here our first term is going to be an x squared. Give us a little bit more room here. So that means this first term is x squared. So it's 1x squared, and then we have 1x minus 12. Now, by luckily picking one of these actual zeros, we were able to simplify from x cubed so that now the polynomial is x squared. Well, once we break this down to x squared plus x minus 12, this is in a form that we hopefully can factor. X times x is x squared. And here, what are the factors of 12? Of course, we'd have 1 times 12, 2 times 6, 3 times 4. So which of these works? Well, it looks like we need a 1x, so it looks like we would use 4 and 3. And what? +4, -3. So then that means x is equal to, if we set this equal to 0, x would be equal to a -4, and here x is equal to +3. And up here, we already found that x equals 1. So here, notice we have all 3 of our zeros. Okay, now that tells us that 1, -4, and 3 are the zeros. Up here, notice we have 1, -4, and 3. So here we had +1, -4, and +3. So there's all of the zeros for this polynomial. And once again, we said there's going to be a total of 3 zeros, and therefore we have our 3 zeros. 1, -4, and 3. Now, could we have looked at the graph of this particular polynomial? Well, let's enter this into the calculator and see what we come up with. We would type in x cubed, so x cubed minus 13x plus 12. And before you continue with the video, you may want to pause this and see if you can put this in the calculator on your own and see if you can get the graph to come out with the right viewing window. So once again, I'm going to start out with Zoom Standard. And it looks like it's going to go off the top of the screen here a little bit at the top. So I'm going to go in and adjust the window. So I need to increase the Y max. And I'm going to go ahead and make that, let's just say 30 and see if that works. And that looks like a pretty good picture of our graph. And once again, if we copy this over, what can we discover here? Well, we found our zeros, 1, -4, and 3. So it looks like here we have -4, 1, and 3. Now, if you notice here, we had all real zeros. There are no complex zeros with imaginary parts. So here, it shows the graph with all 3 of the zeros. Whereas in the previous example, realized that we had 4 zeros, but 2 of them were complex. The graph is not going to be able to indicate the 2 complex zeros. So the graph is only going to be able to give you the real zeros, and in this case, all 3 of the zeros are real. And once again, with your calculator, you could go to second, trace, and we want to find 0, so that's number 2. And of course, you could set your left bound, your right bound, and then we can guess. And notice here we get 1, 0, so there's one of the zeros. And we could do the same thing to find the others, and we know that they're going to turn out to be 3 and -4. All right, so now we have one more example, and here's one that maybe you want to try on your own if you want to see if you can find all of the zeros for this polynomial function. Now, once again, this one is not factored, so we're going to have to try to factor this. And once again, I'm going to show you how we can use p, which is going to be all of the factors of the 25, and then how we can find our q. That would be all of the factors of our largest exponent again, okay? So let me use the same color here. So we have, what are all the factors of 25? We would have plus or minus 1, plus or minus 5, plus or minus 25. And then here we have our q is going to be all of the possible factors here of the coefficient of our largest exponent. So we have x to the 4th. So we would have the factors of 2 would be plus or minus 1 and plus or minus 2. So that means the possible zeros would be all combinations of p divided by q. So of course we could just have plus or minus 1, plus or minus 5, plus or minus 25. That's taking each one of these factors of p, dividing it by 1. Now we need to take each factors of p and divide it by 2. So we'd have 1 over 2, so that's plus or minus 1/2. 5 over 2, so that's plus or minus 5/2. And then 25 over 2 would be plus or minus 25 over 2. So here we have all of the possible zeros. So that means we could randomly pick one of these like we did before, using synthetic division, divide into the polynomial and see which ones will give us a remainder of 0. Now that can be a little time consuming, so we have the invention of the calculator, so we can make this a lot easier. We could simply go to our calculator and type in the polynomial. So we're going to type in the polynomial 2x to the 4th minus 15 x cubed. Whoops, let's see, let me go back. Still in the exponent here. So we have 2x to the fourth minus 15x cubed plus 23x squared plus 15 times x minus 25. And again, I'm going to start with zoom standard. And it looks like the graph is here not showing up all, so we need to increase the y and the decrease the y, so the y max and the y minimum. So I'm going to go into the window, and I'm going to try to make the y minimum. It looks like we need to go down quite a bit, so I'm going to try to say negative 45. And the y max, I think we just needed to go a little bit, so I'm going to try 15. And that seems to work pretty well here, so I'm going to just copy this over. Now, how can this help us find the zeros? Well, we don't even have to worry about all of these possible zeros because we know that we're going to have 1, 2, 3, 4 zeros. And remember, if we look up here, our largest exponent is 4, so that's the total number of zeros that we're going to have. And notice we have 1, 2, 3, 4, so that's all of our zeros. So all we have to do now is go into the calculator, and we can go to second trace, number 2 is 0, and set the left and right bound. So if we go to the first one here, we can set our left bound, go to the right of the point, so go to the right of this point here, set your right bound, and let's see, I didn't move over far enough, so let's see what's going to happen. And if you make a mistake like I did here, notice it says no sign change. That means we didn't properly set the boundary. So let me go back again. Second, calculate. So here I need to move to the left, hit enter, move to the right, make sure we go to the right. So here we are to the right of this point, my right bound, and then we want to guess. And notice we get x equals -1. So x equals -1. And then we go second trace again, number 2 for zeros, move the cursor over, and we can set our left bound, make sure we go to the right of the point, we have our right bound, and then we guess, and we get x equals 1, so x equals 1, and we can go to second trace again, number 2 is 0, and we go over to the next one here, we set the left bound, move to the right of this point, the right bound, then we guess, we get x equals 2.5, x equals 2.5, and then we go to second trace, number 2 is 0, and we have our last one over here, there's our left bound, go to the right of the point, and then we guess, and x equals 5. So here we found all of the zeros. Now, once again, we know that's all of the zeros. There's no complex because we said there's only going to be 4. Now, how could we help this? If that's the zeros, then how can we use this to actually then factor? Now, I do want to point out, let me indicate here that -1, that was one of the possible zeros. +1 was one of the zeros. 2.5, well, 2.5, that's the same thing as 5 halves. So there's a positive 5 halves. That was one of the possible zeros. And then 5, positive 5, is one of our possible zeros. So here, the possible zeros, we will have all the zeros. We just have to determine which one are the actual zeros. Now, once we know the zeros, we could actually use that to factor the polynomial. So in other words, if you look at this and you couldn't figure out how to factor this, well, if we know this is the zeros, if x equals -1 is a zero, that means x plus 1 is a factor. If x equals 1 is a zero, that means x minus 1 is a factor. If x equals 5 halves is a zero, multiply by 2, we get 2x, subtract the 5, that means 2x minus 5 is a factor. And if x equals 5 is a zero, x minus 5 is a factor. So here we have successfully found the zeros and factored the polynomial at the same time. So if you were to multiply all these factors out, you would come up with the original polynomial function. So hopefully now you have a better understanding of how to find the zeros of your polynomial function as well as factoring the polynomial.